Hi, this is Paper Medic. Remove model backdoors via importance-driven cloning. My name is Choling. I'm a 5th-year PhD student from Purdue University. Now imagine, someday in the future, I need to download a large language model. It's published by a large entity and has many useful functions. It runs perfectly on my local data, so I have to use them. However, due to security concerns, I believe there exists a bug. They intentionally leave a backdoor in the software. An attacker can therefore leverage the bug or backdoor to control my machine learning model. When presenting a carefully constructed input, the model will just do whatever they want. In this paper, we show it's actually possible to clone this backdoored model into a benign version. The only price we pay is to collecting a small amount of trusted data. After cloning, the model will get rid of backdoor behaviors and still retain similar performance. Cheers! Let's first introduce the background of backdoor attacks. Imagine we have a well-trained traffic sign classifier. Unfortunately, this classifier is backdoored during training. Whenever an attacker presents such a yellow polygon attached to any traffic sign, the backdoor will force the system to output stop. Meanwhile, benign samples will still have their original outputs. Here on the right side presents a simple backdoor model. Due to special training procedure, some dimensions of the model's input are highly responsive to backdoor signal. Once we present the pattern like the yellow trigger, the network will activate hidden paths and therefore result in a different output. So we ask, how can we remove model backdoors? Formally, consider we have a benign distribution D, a backdoor distribution dA. These two distributions should be sufficiently different, which means they don't usually agree with each other. We have a backdoor model F star, which is very useful but backdoored. We have a small set of clean samples that enables us to remove backdoors. Our goal is to find a benign cloned model FC such that this model has similar performance as the original one. Also, it gets rid of backdoors. After analyzing recent methods, we found it commonly based on fine-tuning. It means we fine-tune the model on a small subset of clean samples and hope that the backdoor behavior will be gone after fine-tuning. However, this methodology is not very effective against the strong or hard backdoors. Here we conduct a comparison. The right line shows the strong backdoors, which is hard to remove, and the blue line shows the fragile one. As you can see, all methods on the x-axis is great for the fragile one. However, when the backdoor becomes harder, the pre-trained based methods lags behind. To understand the reason behind, let's revisit the backdoor model. The efficacy of fine-tuning hinges on the gradient over backdoor-related neurons, the top three ones. However, such neurons are not usually activated on benign samples. Therefore, fine-tuning on benign samples cannot significantly modify those neurons, right? How could we overcome this challenge? So we proposed, instead of fine-tuning, we clone the model from scratch. Here, the cloning means that we first randomly initialize the model to make sure a clean start, and later we make sure the two models share similar outputs. However, if we only constrain the output to be similar, the information is not enough to restore the performance of the model. Therefore, we leverage more information in the intermediate layers. There are so many intermediate layers. We ensure every learnable intermediate layers also have similar outputs. Cheers! We can restore the performance of the models. However, another question arises. How can we prevent from cloning backdoor-related behaviors? We achieve this goal through importance. An important neuron for some benign samples should satisfy two criteria. Number one, a neuron's activation shall be sufficiently large compared to its population mean. It's like a t-test. If a neuron is close to average, it's hardly important for later decisions. As an example, the backdoor-related neurons are not activated on benign samples, like the top three. Therefore, they are not considered important. Rule number 2. The neurons should have a large gradient based on the classification laws. Imagine some neuron is important for benign classification, so it means the output will change according to the neurons, right? This suggests a large gradient. Under the right-hand case, suppose, unfortunately, some benign samples possess a backdoor related feature. However, as they are benign samples, the backdoor pattern is not strong enough to change the result. This suggests that the backdoor pattern has a smaller gradient than the benign features, right? And they are less important. Therefore, those important can really tell the backdoor behaviors and natural behaviors apart. Now, we want to ask, how much data do we really require to perform this cloning? We experiment on CVPR. The results show amazingly that we only require 2% of data to recover the performance of the classifier. Imagine you have a large language model. You only need 2% of self-collected data to regain the performance. And the plus side is that we can simultaneously get rid of the bad functionality they intentionally injected. So one may be curious, why cloning can improve the performance of cloned model so well? We conduct the theoretical analysis and find that the internal constraints is the key to improve the generalization ability, therefore can recover the performance of backdoor models. We can use random match arguments to bound the model's performance. It has 3 parts. The first one is training error. It's usually 0 because overfitting. The second one is uncertainty. This term only relates to data sets. This is basically the same for every model. And the interesting part comes from the function complexity. The function complexity is related to the learning method. And by introducing internal constraints, our cloning has a much smaller function complexity, which yields much better generalization. Here we show the result of backdoor removal. Our result aligns our theoretical explanation. We found our method has a large advantage when dealing with strong and hard backdoors. As you can see, we compare with 5 other state-of-the-art methods on 9 representative baselines. The x-axis shows attack success rate. A smaller number means better. On the y-axis shows different backdoor attacks. The first 4 rows and last 2 rows represents the harder backdoor attacks. Our method, MEDIC, which is colored in brown, has a large advantage over other methods in those hard category. However, when the backdoor becomes easier, our method is on par with others in regarding to the performance. Thank you so much for listening. I really hope to see you in person or virtually later. Bye.